Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 10 Electromagnetism. We will be discussing about the magnetic effects of electric current. Are you all ready? Let's start. Electromagnetism. This is today's topic. Here we know that a bulb glows when electricity flows through it. How does a bulb glow? When you on the switch, or a small LED bulb which is connected to a battery glows. There is flow of current. There is electricity which helps the bulb glow. Here in this figure you can see a bulb. Okay. Neither there is a battery nor no switch is connected to it. Okay. This bulb is going to glow. How you know? When I bring this magnet close to it, the bulb is going to glow. Okay, and the reason behind this is electromagnetism. So after today's class, you will understand what electromagnetism is and how a magnet can help a bulb glow without a battery or without a current flowing through it. Are you ready to understand this? Yes. The relation between electricity and magnetism. The study started with an experiment, and the experiment was performed in the year 1820 by a famous scientist, Hans Christian Oersteds. So this is Hans Christian Oersted. So we call it Oersteds Experiment. Let's see what was Oersteds Experiment. That is, according to this experiment, using an electric current, you can produce magnetic effects. Okay, when electricity flows through a wire, it can produce magnetic effect. This was his observation. Okay, here what he had done was, he took a wire which was connected to a battery, then a key, a meter and a rheostat. Okay. So this is his wire XY. This XY wire is connected to all this. When the key is plugged in, what happens? Electricity starts flowing through it. Okay. Due to this electric flow of current, that is, when current flows through this conducting wire, what happened was, he took a compass needle. This is how a compass looks. Okay. And compass is a device which is used to find the direction of magnetic field. Okay. This is how a compass looks. It has the north and south. Normally, if there is no deflection, if there is no magnetic field, it will be in the north-south direction. This will be at the north and this will be at the south. If there is any magnetic field, it will have deflection. Okay, so here he used a compass in order to find the direction of magnetic field. So when there is a deflection in this compass needle, what does it mean? There is a magnetic field, right? So when he brought a compass close to it, what he observed was, in the compass there was a deflection. Initially there was zero deflection, there was no deflection, but when he brought this compass close to this wire, there was deflection, which means when electricity was made to flow through the conducting wire, it has produced magnetic effects. Okay, this was his observation. Okay, using a compass needle, he found out that there is magnetic field produced around the wire. Okay, so the relation between this electricity and magnetism was studied by him. What are his observations? So first, you can see this is how the setup is. You have a wire AB. This wire AB is connected to a key, a battery and a rheostat. Okay, here you can see the directions given. This is north, this points towards south. Here you have west and this is east. In case of wire, we are considering. Okay, now here we have 5 images given. Let's see what they are. The first one is when the key is open. That is, you are not giving the key. You are not plugging in the key. If you don't plug in the key, you will understand that there is no current flowing through it. Okay, when the current is not flowing, your compass needle will align in the normal direction, that is in the north-south direction. This is the normal alignment. With respect to the Earth's magnetic field, it will be aligning in the north-south direction. Okay, now the second one, when the key is pressed. When key is pressed, what happens? You are giving the key. What happens? Electricity or current starts flowing through it. When current flows, you know, magnetic field is created according to this experiment. Okay, the presence of magnetic field can be determined by using the compass needle. So here the compass needle is placed just below the wire. Okay, it is placed below the wire. In that case, you can see the north pole of this compass needle will move towards the west. Okay, you can see it deflecting towards upwards direction. Here it is the west. Towards west, it will align. Okay, now if you are increasing the current, we know if current is increased, what happens is the magnetic field also increases. They are directly proportional. When current increases, magnetic field also increases. The increase in magnetic field can be determined just by looking at this compass needle. The compass needle deflection will increase. Okay, initially if the deflection is this much, what happens is the deflection will increase. It can happen in this way. Okay, more deflection towards west, it gets deflected more. Now the third one is when the direction of current is reversed. So here you can see this is how the current is positive terminal, negative terminal. Okay, here you are reversing the battery, you are reversing the direction of current. Now in this case, the current will be flowing in this direction. Yes, from A to B the current will be flowing. Now what happens when you reverse it? The direction of current will be in this way from B to A. What happens to the magnetic field? Deflection in the compass needle. Here what happens is the compass needle is again placed just below the wire and it will get deflected towards the east, okay, downwards towards east. Again, if you are increasing the current, what happens? Deflection will increase. Initially, if it was in this manner, the deflection, it would have increased more. Okay, so this is your third point. Now the fourth one, if the compass needle is placed just above the wire. In all these three cases, you are placing the compass needle below the wire. Okay, it is shown using dotted lines. Dotted circles are shown. Okay, now when the compass needle will be placed above the wire, what happens is just opposite thing will be happening. Okay, here you can see the deflection is towards north. When normally, that is without reversing the current, without reversing the battery, you can see towards north it is. Towards the west, the north pole of the magnetic compass needle is deflecting. Okay, now what happens is just opposite, that is towards east this deflection will happen. Okay, towards east the north pole of the magnetic compass needle will point. Okay, now the fifth part is when the opposite, that is opposite this will happen, that is when you are reversing the current and placing the compass needle above it. Here you can see proper circles. Okay, these three cases you have dotted circles. So here what you can see is, in this case it was towards the north pole of the compass needle is getting deflected towards east. Here it will be towards west, just the opposite. So these are the observations of Oersteds experiment. Okay, remember Oersted performed this experiment. In this experiment, the main observation was when current flows, magnetic field is produced around the current carrying wire. Okay, let us understand what magnetic field is and what are magnetic field lines. So here we are taking the case of a simple bar magnet. For a simple bar magnet, we have studied about them. So here you will be having a north pole and a south pole. Okay, we know that north pole repels each other, south pole repels each other, north pole attracts each other. Okay, now here you can see some lines and these lines are called magnetic field lines. The first point is magnetic field lines are imaginary lines. You cannot actually see them, they are imaginary lines. Second, magnetic field lines start from north pole of a magnet and end at the south pole. Okay, this is the direction of magnetic field lines. They are starting from the north pole and moving towards the south pole, outside a magnet. When you take the case of inside a magnet, magnetic field lines move from south to north. This is how the direction is. Okay, inside the magnet. Third point, unlike the electric field lines, magnetic field lines are closed curves. So you can see these are closed curves starting from here, ending here. So you can see closed curves. Okay, so when you take electric field, you will be having a positive charge, you will be having negative charge. Okay, in these cases, the field will be either going out or it can be inward. Okay, next, the tangent at any point on the magnetic field line gives the direction of magnetic field at that point. To find the direction of magnetic field, for example, you need to find the direction of magnetic field at this point. You will have to just draw a tangent and the tangent will give you the direction of magnetic field at that particular point. Two magnetic field lines never intersect each other. This is a very important point. If they intersect, let's say you have two magnetic field lines which intersect each other. Okay, if they intersect each other, it means that at this point there will be two directions of magnetic field, which is not possible. Therefore, remember this point, two field lines can never intersect each other. Okay, magnetic field and field lines due to current in a straight wire. We will discuss an experiment. Here, what you need is a rectangular sheet of paper or a cardboard. Then you need some iron filings, a wire. This is variable resistance or rheostat. Then you need an ammeter, battery and key. Okay, so this is how the connection is made. You will first take this cardboard piece, make a hole in it and pass a thick copper wire. Copper wire is a conducting wire which can pass electricity to them. Okay, so take a copper wire and pass through the hole which is made on the cardboard. Okay, next you are making a connection, that is your circuit is complete with a variable resistance. Then you have an ammeter, then a battery. Remember, while connecting ammeter and battery, the positive of ammeter should be with the positive of battery. Clear? Then you have a key. Okay, when the connection is given, before that you will have to spray some iron filings. Okay, iron filings you are spraying over here on this cardboard. Now let's see what happens when current flows through it. Okay, current flows means you are plugging in the key. When key is plugged in, electricity starts flowing in the opposite direction of flow of charges. Okay, charges flows in one direction, that is electrons flows in one direction and electricity flows in the opposite direction. Okay, there will be deflection in the ammeter, which means that there is a current flowing through it. Okay, so here you can see through the copper wire current is flowing. When through the copper wire current is flowing, we have studied Oersteds experiment. What did he say? A current carrying wire will produce magnetic field. So here magnetic field is produced. Due to this magnetic field, what happens is the iron filings gets arranged. Okay, this is how the iron filings gets arranged. Okay, in this pattern, that is concentric circles pattern, the iron filings will get arranged. So how do you detect there is a magnetic field in this case? Here you will be taking a compass needle. If you are placing compass needle somewhere here around this wire, what happens is there will be deflection in the compass needle. Okay, and the north of the compass needle, in which direction it points, shows the direction of the magnetic field at that particular point. So this is the experiment which is performed. Okay, here you can have a wire and we are finding magnetic field that is produced due to a conducting long wire. Clear? Let's see what are the observations. The first observation is the magnetic field lines form the concentric circles around the wire with their plane perpendicular to the straight wire and with their centers lying on the wire. So you can see in this diagram it is very clear that this is your wire. Okay, and if you have a wire like this, and this is how the cardboard is. Okay, through this cardboard the wire is being passed out. Now what happens? You have the iron filings which is put here. They get arranged in the form of concentric circles. What are concentric circles? Circles with same center. Okay, so these are concentric circles. If you are drawing with a compass, you will be keeping the compass here, okay, and changing the radius and drawing many circles. So these are concentric circles. You can see concentric circles and the iron filings will be getting arranged in the form of concentric circles. Okay, and you have to remember the plane. This plane is perpendicular to the wire. Okay, so this is your first observation about the arrangement of iron filings, about the nature of the magnetic field lines we are predicting. Clear? Second observation, when the direction of current in the wire is reversed, the pattern of iron filings does not change, but the direction of deflection of the compass needle gets reversed. How do we change the, how do we reverse the direction of current? Here you have a battery. Okay. If you change this positive and negative terminal, you are exchanging it. Negative comes here and positive goes here. You will have to change the ammeter arrangement also. So then what happens? You are reversing the current. Okay. When current is reversed, what happens? When current is reversed, there is no change in the pattern of arrangement of the iron filings. They will be the same. But what happens here is the current direction is changing. Now, if the current is flowing in this direction, now the current will be flowing in the opposite direction. This is what happens. Okay. Also, what happens is the deflection in the compass needle is going to change. Okay. Magnetic field direction is going to change. If the magnetic field, it was deflected in this direction, the magnetic field, north pole of the compass needle was deflected in this direction. Now what happens? It will be deflected in the opposite direction. So change in deflection will happen when the current is reversed. Okay. Third observation, on increasing current in a wire, the magnetic field lines become denser and iron filings gets arranged in circles up to a larger distance from the wire, showing that the magnetic field strength has increased and it is effective up to a larger distance. So here what happens is you are increasing the current. When current increases, what happens to magnetic field? According to this observation, when current increases, magnetic field also increases. The magnetic field strength increases. Now what happens is more denser circles will be formed. Okay. More closer the concentric circles will be, and for a longer distance you can see these circles being formed, which means there is a strong magnetic field. Magnetic field increases means what happens? More iron filings will get arranged in concentric circles near to the wire, close to the wire, okay, showing the denser. Okay, here there will be more density. There will be more denser. The arrangement of the iron filings will be more denser in the form of concentric circles when the current increases, showing the presence of a strong magnetic field at that point. Clear? We have studied that to find the direction of magnetic field, we are using a compass needle. Okay. Without compass needle, theoretically, we can find the direction of magnetic field. For that, we have a rule called right hand thumb rule. If you have studied right hand thumb rule, you can find the direction of magnetic field without using a compass needle. The statement is, if we hold the current carrying conductor in our right hand such that the thumb points in the direction of flow of current, then the fingers encircle the wire in the direction of magnetic field lines. You just need to use your right hand. Okay. In the right hand, you have to point the thumb in such a direction in which the current is flowing through the conductor. The direction of flow of current through the conductor is shown by the direction in which you are holding your thumb. Okay. When you hold it in this way, you will be having the fingers which encircle around it. Encircle around the thumb. So this will be giving you the direction of magnetic field. So here thumb points in the direction of current and the fingers which wrap around it shows the direction of magnetic field. So here first, if in the upward direction you have the current. Okay, so this is how current flows in a conductor. Okay. So you can see the direction of magnetic field. This is how the direction of magnetic field is. So consider your right hand. So this is how you are holding the conductor and you will be having the direction of your fingers. Okay. So here it is in this way, that is the upper part. Okay. The lower part in this direction. So when it reach here, it will be in this direction. Clear? When you are holding it in this way, that is towards the downward direction, you are holding the conductor. That is, the current is flowing through the conductor in this direction. Then what happens? This is how you will be holding your hand. Okay. You can see the fingers which wrap around it. Okay. So here, this is the direction and the upper part in this direction. Okay, you can see this. Clear? So here you have the thumb in the direction of current and the magnetic field is in the direction in which the fingers, the other four fingers points. Okay, so this is your right hand thumb rule. Next, magnetic field in a circular loop or a current carrying loop. Here you can see a circular loop. Take a wire, a thick wire, and bend it in the form of a circular loop. So we have studied the magnetic field, how the magnetic field lines will be arranged in case of a straight current carrying conductor. The straight current carrying conductor is now bent in the form of a circular loop. And now let's see how the magnetic fields gets arranged. Okay, so here you can see the loop. We have taken a cardboard. Okay, in this cardboard, 2 holes are made and this loop is passed through the cardboard, through the holes. So here you have 2 holes. Through the holes, the loop is passed. Okay, now it is connected to the positive and negative terminal of battery. You will be having the key, rheostat, ammeter, etc. Okay, now what happens? Here, when the current flows, we have studied the thumb rule. Yes, when the current flows, there will be magnetic field. We know that when current flows through a conductor, there is magnetic field created. Oersteds experiment we have studied. Okay, so here again, when the current flows through this loop, there will be magnetic field produced. Now, on this cardboard, we are spraying or we are sprinkling some iron filings. What happens to the iron filings then? These iron filings will get arranged in a definite pattern. And this is how the iron filings gets arranged. To find the magnetic field at a particular point, you will be using a compass needle. When the compass needle is placed somewhere here, the direction in which the north pole of the needle points will show the direction of magnetic field at that point. So this is how we will be getting again concentric circles, and this is how the iron filings will get arranged around the circular loop. Okay, this is a pattern of arrangement of the magnetic field lines. Clear? Let us see the properties of magnetic field lines which are formed in case of a circular loop. So here, the first point, in the vicinity of wire, the magnetic field lines are nearly circular. So you can see around the wire, close to the wire, you can see complete circles, concentric circle up to here. Okay, up to a particular distance, you will be having complete circles. So this is the first point. The pattern in which the iron filings gets arranged, or the direction, the magnetic field arrangement will be circular, very close to the wire. Okay. Second point, within the space enclosed by the wire, the magnetic field lines are in the same direction. Okay. Around this wire, you can see. Okay. At this, when you take this part, you can see the field lines in the same direction. This is the direction in which they are moving. That is, when you are holding like this, the thumb current direction, this is a current direction, and the field direction is in this way. Okay. Next, when you take this case, here the current is flowing in this direction. Current in the direction of thumb shows the direction of current. Then you will be having the fingers will be showing the direction of field. Okay. So here it is in one direction and here it is in the other direction. Next, the third point, near the center of the loop, the magnetic field lines are parallel to each other. Okay. So this is the loop. Okay. Here when you take, this is the loop, it will be having a diameter. Okay. At the center, nearly the center of loop, what happens is, the distance will be increasing. The field distance from the wire will be increasing, which means here and all you will be getting straight parallel lines, almost parallel lines you will be getting. The field lines will be parallel to each other. This is the third point. At the center, magnetic field lines are along the axis of the loop and normal to its plane. Okay. So this is the axis of loop. At the center, it will be along the axis of loop and it is perpendicular or normal to its plane. Plane, this is your cardboard plane. Okay. And this is a plane in which you have the circular loop. So here you can see, when you take a 3D image, you can see that they will be perpendicular to each other. That is the axis, the plane in which the field lines is arranged, and your loop will be perpendicular or normal to each other. So these are the 4 points. Fifth point, magnetic field lines become denser if first one, strength of current in loop is increased. That is, when the strength of current increases, what happens is the pattern. For example, so this is your loop and this is the initial arrangement. Okay. So this was how the iron filings got arranged. Now when the current is increased, what happens is more denser fields will be formed. Okay. Field lines will become very closer and more denser. More field lines can be obtained. So increasing the strength of current in loop, what can be increased? The magnetic field can be increased, and this is obtained. That is, you can understand this strong magnetic field, how the arrangement of the iron filings. Okay. So the next point, the number of turns in loop is increased. So here you are taking the case in which there is only a single turn. Okay. That is, you are taking a straight long conductor and it has been bent in the form of a loop. When you are increasing the number of turns, so 1, 2, 3, 4, like this, when you are increasing the number of turns, again what happens is the magnetic field increases. First one, current increase. Second, the number of turn increase. What happens? Magnetic field also increases. Okay, so this is a fifth point. Sixth one, magnetic field lines pass through the loop in same direction. They appear to come out from the face of loop on other side, so that face behaves as north pole, while the magnetic field lines appear to enter in at the front face of loop, so it behaves as south pole. We'll be explaining this in detail. Now just understand, here you can see the pattern of field lines. Okay, it is somewhat like this. Okay, and here you can see the pattern. Okay, in this way. So here this is the part and this is the other part. Here one direction and the other direction. Okay, so this is one phase, the arrangement of field lines. The other phase arrangement is in this way. That is, when you write in S. So here you can see this part and this part. Okay, this is the arrangement. So here when you get in the form of an N, you can see, and I'm starting from here. Okay, so this is in the form of an N. The field lines are in the form of an N. Therefore, this part will be the north pole. It will be acting as a north pole. And this part, which is in the form of S, the field lines arrangement is in the form of S, is the south pole. Okay. So, in the case of bar magnet, we have two poles, north pole and south pole. We call it dipole. Here again, in case of a circular loop, current carrying circular loop, you are getting a north pole and a south pole. So, here again you are having a dipole. So, this is again a dipole. two poles exist, then there is a dipole. Also, we know that the magnetic monopoles can never exist. Okay, now we have the clockwise rule. Looking at the face of the loop, if the current in the wire around that face is in anti-clockwise direction, the face has the north polarity. So check this picture. Here, this is north magnetic pole. Okay, what is counterclockwise or anti-clockwise current? How can you show it? So here, you can see that this is the clockwise direction. Okay, this is how clockwise direction is. Okay, you will be having, in case of a clock, you will be having 12, 3, 6, 9. Okay, and this direction, the needle will be moving in one direction, and this direction is a clockwise. Okay, what about counterclockwise? Counterclockwise will be in the opposite direction. Okay, now here you can see that in case of counterclockwise current, counterclockwise means opposite to clockwise. This is a counterclockwise or anti-clockwise current. In case of anti-clockwise current, you will be getting a north magnetic pole. This is your north magnetic pole. Okay, so here when you're holding your thumb in the direction of the current flow. Okay, this is the direction of current flow. Fingers direction. You can see fingers direction. It is going down, coming up. Okay, so this is your north polarity. Clear? Counterclockwise, north magnetic pole. Okay, when you have clockwise current, this is a clockwise direction of current. Clockwise current. In this direction, you will be having clockwise current. When you have clockwise current, take your thumb. This is clockwise current. You can see the direction of magnetic field. When you take, you will be getting the south magnetic pole. This is in the form of an S. S means south pole. This is in the form of N. N means north pole. Okay, you can see here. So this direction from here at this point, when you keep, you will be having showing this direction. When you keep here, you will be having this direction showing. Okay. So this is about the relation between counterclockwise current and the north pole, clockwise current and south pole. Okay, so this is your clockwise rule. Magnetic field due to a solenoid. We have studied the magnetic field due to a current carrying straight wire and a circular loop. Now what is a solenoid? First we need to understand what a solenoid is. How a solenoid is formed. To form a solenoid, you have to take an insulated copper wire which is wound in the form of a cylinder. Okay, in the form of a cylinder. So this is a cylindrical shape. In the form of cylinder, when you take a insulated copper wire and wind it in this manner with many number of turns, you will be getting a solenoid. This is what a solenoid is, how the solenoid looks like. Okay, so a solenoid is a long coil containing a large number of closed turns of insulated copper wire. The diameter should be comparatively very less to the length of the wire. Okay, now again we will be doing the same arrangement which we have done in case of a straight long conductor and circular loop. Take a cardboard. On the cardboard, make two slits. So here holes are not enough. You will be making two slits and pass the insulated copper wire in this pattern. That is, you will be making the solenoid. Give the connection. You will be having battery. You will be having the key, rheostat, whatever is required. Okay, then what should be done? We will be giving the current is made to pass through it. That is, plugging in the key, current will start flowing through this. Okay, when current flows, what happens? Magnetic field will be produced. Okay, so this is how the magnetic field lines will look like. Okay, that is, you will be sprinkling the same iron filings on the cardboard and tap it gently. What happens? Iron filings will be getting arranged in a definite pattern, and this is the pattern in which the field lines get arranged. Okay, so you can see this is a north and south. You can see from north to south, north to south, north to south. Again, circular loops you can see in this case also. At the middle, you will be seeing parallel lines. Okay, this is how the field lines will be going out and coming in. So here, you won't be getting complete circles because the distance is increasing. The field strength will be decreasing. Okay, here there is strong field. Therefore, you will be getting complete circles, complete closed circles. Okay, but here what happens? You can see only the going out of the field lines and coming in of the field lines. Why? Because the strength is decreasing. Strength is decreasing because the distance is also increasing. Clear? What are the properties of the field lines which are formed in case of a current carrying solenoid? First one, magnetic field lines inside the solenoid are nearly straight and parallel to the axis of solenoid. Outside you can see they start from north and go to the south. Inside you can see parallel lines. So these are the magnetic field lines. You can see the parallel lines. Okay, so these are the magnetic field lines from south to north inside a solenoid. Second point, the magnetic field lines become denser on increasing current in the solenoid. The same point we have discussed in case of circular loop. When current increases, the strength of current increases. What happens to magnetic field lines? Magnetic field lines will increase, which means the magnetic field will increase. That is, you will be getting more denser concentric circles. Okay, it will be more denser at these places. Okay. More field lines you can see in this case. Now the third point, the magnetic field is increased if the number of turns in the solenoid of given length is increased. So here if you take two solenoids, this is your first one and this is your second one. Okay, so here you can see in the second case, the number of turns is increasing. When the number of turns increases, what happened to magnetic field? Magnetic field also increases. So two things that can be done to increase the magnetic field. One is increasing the strength of current and the second is increasing the number of turns. Okay. Now the fourth one, the magnetic field is increased if a soft iron rod is placed along the axis of solenoid. Okay. Next, how the magnetic field can be increased is along the axis of the solenoid. So you are winding the insulated copper wire, right? So here inside this, along this axis, if you are placing an iron nail, what happens? The strength will get increased. The strength of magnetic field will increase. So this is your fourth point. Here again you can see the north and south pole can be determined. How it can be determined is if it is anti-clockwise current, then north pole, clockwise current, south pole. So this polarity can change when the battery is reversed. Okay, the current direction is reversed. Now, if the battery is in this manner and you are reversing it, that is, you will change in this way. What happens? Current flow also will change. If the current is flowing in this direction, now what happens? We know that the direction of current is opposite to the direction of electrons. So here, electrons will be flowing in this direction, current in the opposite direction. Okay, positive charges direction, current will be flowing. When you are reversing, negative comes first and then here you will be having positive. In that case, charges or the electrons will flow in this direction, opposite direction, current will be flowing. Then what happens is, here we have north pole and this is the south pole. If the current is reversed, here you will be getting south pole and here you will have the north pole. Okay, so remember these points about the properties of magnetic field lines formed in the case of a solenoid. We have discussed about the field lines formed in the case of a bar magnet and the field lines which are formed in the case of a solenoid. Let's see what are the similarities between the magnetic field lines formed in case of solenoid and the magnetic field lines in case of a normal bar magnet. First point, the magnetic field lines of a current carrying solenoid are similar to the magnetic field lines of a bar magnet. In bar magnet we have discussed, you will be having north pole, south pole. Okay. Outside the magnet, the field lines will be in this direction, north to south, north to south. Okay, so this is the direction in which outside the magnet you will be having field lines. Similar case you got in case of a solenoid. Solenoid also, we had north and south poles. The field lines were arranged in a similar pattern. Okay, inside we had parallel lines. In case of bar magnet, you will be having parallel lines which move from south to north. Here again, you will be having parallel lines south to north. Okay. The second point, a current carrying solenoid when suspended freely sets itself in the north-south direction exactly in the same manner as a bar magnet does. Okay. So, we have discussed in case of bar magnet, always the north pole, south pole, they will be getting arranged in a north-south direction. The bar magnets will be getting arranged, that is freely suspended. Because of Earth's magnetic field, they will get arranged in a north-south direction. Same will be the case of a current carrying solenoid. When freely suspended, it will get arranged in the north-south direction because of the Earth's magnetic field. Okay. Third point, a current carrying solenoid also acquires attractive property of a magnet. That is, a current carrying solenoid can act as a magnet. When you bring a safety pin or some metal piece in vicinity of this solenoid, what happens? It will be getting attracted to the solenoid. Why? Because this current carrying solenoid is now acting as a magnet. When electricity flows through a solenoid. Okay. Solenoid we know is a long copper wire which is wound in the form of a cylinder. Okay, when current flows through it, it acts as a solenoid, and then you can see that this solenoid will be acting as a magnet. It has gained the attractive property like the normal bar magnet. So these three are the important points when you take the similarity between a solenoid and a bar magnet. We discussed the similarities. Now the dissimilarities between a current carrying solenoid and a bar magnet. First point, the strength of magnetic field due to a solenoid can be changed by changing the current in it, while the strength of magnetic field due to a bar magnet cannot be changed. Okay, when you take a bar magnet, we know that this bar magnet has north and south poles and there is no battery connected to it. There is no current flowing through it. It has its own magnetic field. Okay, but in case of solenoid, we know that it can produce a magnetic field only when a current carrying solenoid is connected to a battery, a key and a rheostat. Okay, so when the key is plugged in, what happens? The current starts flowing and it can create a magnetic field. To increase the magnetic field, what can be done? Magnetic field can be increased. Magnetic field strength can be increased when the current is increased. On increasing the current, magnetic field can be increased. Okay, this cannot be done in case of bar magnet. It will always remain the same. Now the second point, the direction of magnetic field due to a solenoid can be reversed by reversing the direction of current in it, but the direction of magnetic field due to a bar magnet cannot be reversed. This point also we have discussed in case of solenoid. When you are reversing the current, that is initially if the battery is in this way, you are reversing it. Okay, negative and positive are connected opposite. What happens? The direction of current flow is changing. Okay, when you reverse the battery, there is reversing of current. The current direction will change. Initially, current will be flowing in this direction. Here, the current will be flowing in this direction. What happens to the magnetic field then? The direction of magnetic field also changes. But in case of bar magnet, we don't have anything to reverse. Okay, north pole, south pole will remain the same, and the bar magnet, the magnetic field produced will always be in the same pattern, same direction. Okay, north-south direction, they will be getting aligned. Clear? So these are the two important dissimilarities between the magnetic field produced by a bar magnet and a current carrying solenoid. What is an electromagnet? As the name suggests, electromagnet, a magnet which is formed with the help of electricity is called an electromagnet in simple words. So we have studied about solenoid. Okay, this solenoid, in case of solenoid, when electricity is passed, it is connected to a battery, and when electricity is passed, you know that magnetic field is produced. When this electricity is stopped flowing, that is when the switch is off, what happens? There will be no current, there will be no magnetic field, which means this solenoid can act as a temporary magnet. Okay, this acts as a temporary magnet. Okay, this is a temporary magnet. It can attract materials. It can attract metals to it. Okay, so using a solenoid, you can form a temporary magnet, and the solenoid will be acting as an electromagnet. We have studied to increase the magnetic field. What can be done? An iron nail can be placed along the axis of the solenoid. Okay, when you take it out for some time, it can attract some small pieces of iron, small pieces of metals, safety pin or iron filings. These materials it can attract for some period of time because it is acting as a temporary magnet. Okay, an electromagnet is a temporary strong magnet made by passing current in a coil wound around a piece of soft iron. So you have a soft iron and here you have a wire which is wound over it, and this is an artificial magnet. Why is it called artificial magnet? After some time it will be losing its magnetic properties. Okay, so this is what an electromagnet is. Ways of increasing the magnetic field in case of a electromagnet. We know to increase the magnetic field in case of a current carrying loop, then in case of a solenoid. So first point is by increasing the number of turns of windings in the solenoid. We are using a solenoid to make an electromagnet. So if you have two solenoids, okay, the one with maximum number of turns can produce more magnetic field. So this is the first point, to increase the number of turns. Second, by increasing the current through the solenoid. This point also we discussed. That is, when current increases, what happens? On increasing current, the magnetic field strength also increases. So these are the 2 points, increasing the number of turns and increasing the strength of current. Okay, what are permanent magnets? We have discussed about temporary magnet, how electromagnets act as a temporary magnet. Using a soft iron, we can make an electromagnet which is a temporary magnet. It cannot retain its magnetic property once the flow of current stops. Okay, for a very short period. If it is retaining, even it is for a very short period of time. Now, permanent magnets are naturally occurring magnets. That is, they have the magnetic property always. These are called permanent magnet. Permanent magnet is a naturally occurring magnet. The magnets that we are using, simple bar magnet, these are examples of permanent magnet. Okay, permanent magnets are used in electric meters, galvanometer, ammeter, voltmeter, and in magnetic compass. In these places, we are using a permanent magnet. Now, we know that using a soft iron is taken and around this it is wound with the insulated copper wire connected to battery, then to key. When key is plugged in, current starts flowing through it and it gains magnetic properties. Okay, and in this setup, it can act as a magnet. When the current stops flowing, what happens? The magnetic property is no more. There is magnetic property here. But in case of a permanent magnet, how we make a permanent magnet is using a piece of steel. So take a piece of steel, okay, insulated copper wire is wound over it, connected to a battery, then a key is plugged in, electricity starts flowing, current starts flowing through it. When current starts flowing, the steel piece starts gaining magnetic property. It starts to get magnetized. Okay, it starts to get magnetized. Even if the current stops flowing, that is, we are removing the plug key, current will stop flowing through it. Okay, then still this piece of steel will be having the properties. It will have the properties, magnetic properties for a long period of time. So we say that in case of steel, it is having high retentivity. Okay, retentivity is a word. It is a property to retain its magnetic properties even after the flow of current stops. Okay, so this is what a permanent magnet is. Now let us make a comparison between an electromagnet and a permanent magnet. We studied what an electromagnet is and what a permanent magnet is. First point, it is made up of soft iron. Okay, what is permanent magnet made up of? It is made up of a steel piece. Second, it produces a magnetic field so long as current flows in its coil. Once current stops, what happens? It can no more act as a magnet. Okay, it produces the temporary magnetic field. There is only a temporary magnetic field produced. It is acting as a temporary magnet. Now the second, in case of permanent magnet, it produces a permanent magnetic field. Even if the current stops flowing, still then it has the magnetic property. The steel piece will be magnetized and it can show magnetic properties. It can attract metals to it. Third point, the magnetic field strength can be changed. Yes, that is, how can you change? In case of electromagnet, the number of turns in the solenoid can be increased and the current strength can be increased. Here, the magnetic field strength cannot be changed. Why? Because this is a permanent magnet. Once you remove it from the coil, okay, we know that current is not flowing anymore and it has gained the magnetic properties. And this magnetic properties will remain the same. You cannot change the magnetic field. The magnetic field of an electromagnet can be very strong. It can produce very strong magnetic field. How can it produce? Because when the current increases or the number of turns increases, accordingly the magnetic field also increases. Therefore, strong magnetic field can be produced. The magnetic field of a permanent magnet is not so strong. Because when you make a comparison, it is not much strong because there is no current flow or there is no number of turns. There is no dependence for a permanent magnet. Next, the polarity of an electromagnet can be reversed. How to reverse? That is, when the battery is reversed, the current flow is reversed, north and south pole will get exchanged. The polarity of a permanent magnet cannot be reversed. That is permanent magnet. The best example is simple bar magnet. It will be having a north and south pole. Okay, it will remain always the same. It cannot be changed. Polarity cannot be changed. It can easily be demagnetized by switching off the current. It can act as a magnet only when current flows through it. When the current stops flowing, it gets demagnetized. The magnetic properties will get removed. Okay. Now, when it comes to the case of permanent magnet, it cannot be easily demagnetized. You cannot remove the magnetic properties from that material which is magnetized. Okay. Now, when you are asked to write the advantages of an electromagnet over a permanent magnet, what are the advantages? Let's see. The first, an electromagnet can produce a strong magnetic field. Why? Because it is depending on the current and the number of turns. Then the strength of magnetic field of an electromagnet can be easily changed by changing the current in its solenoid. The strength of current increases, magnetic field also increases. When strength of current decreases, magnetic field also decreases. So this is the second point. The polarity of the electromagnet or the direction of the field produced by it can be reversed by reversing the direction of current. Okay, when current direction is reversed, battery's terminals are changed. What happens? Current direction, the flow of current will be in opposite direction. Similarly, what happens? The polarity changes. Initially, if it was north-south, now it will become south-north. Okay, this exchange will happen in polarity. So, these are the advantages of an electromagnet compared to a permanent magnet. What are the uses of electromagnet? First, for lifting and transporting heavy iron scrap, plates, etc., particularly when it is not convenient to take the help of human labor. So, better than human labor, it can lift and transport heavy materials like iron scrap and the plates. Okay, for this purpose you are using electromagnet. Second, for separating iron pieces from ores when iron exists as impurities. We have learned about ores. So, in case of ores, there will be chances of impurities. If iron is existing as impurity, using an electromagnet, you can attract these iron pieces and remove the iron content from the ore. For removing the pieces of iron from wounds, if in your body you got some injury due to some accident or something, if there are iron pieces, these iron pieces can be attracted using an electromagnet and removed. Okay. In scientific research, to study the magnetic properties of substances in a magnetic field. So, substance which are in magnetic field, its magnetic properties can be studied using an electromagnet. In several electrical devices where they are used, one is electric bell. In case of electric bell, that is school bells and all, these are being used. Then in telegraph, then electric tram, electric motors, microphones, loudspeakers. In all these devices, you have the electromagnet which is being used. That's all for today. In today's class, I have given you an introduction to electromagnetism. We have studied the magnetic field in case of a long wire, conducting wire. Then the magnetic field which is produced in case of a circular loop, and the magnetic field in solenoid. We have studied about electromagnets, right hand thumb rule. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai, पर best hai. Thank you.